Hello everyone, welcome to Maths IEC. Today we are going to discuss about EMF and internal resistance. Now, here are some basic things that we need to establish before we go ahead. All cells and batteries have a value for their EMF. So the definition of EMF is the amount of energy supplied by the source per unit charge. So this comes from the formula V is equal to E divided by Q, or W divided by Q. Energy over charge or work done over charge. Internal resistance is the hindrance or the opposition to the flow of charge within a power supply. Now, when you make a power supply, like a cell, we include different parts of metal. So obviously there will be some internal resistance. Now, a part of that internal resistance is that you can't avoid it. And the other thing is we need to introduce some internal resistance for the safety. Now, let's just look into this a little bit more. So imagine if you had a battery or a cell with very small internal resistance. Now, remember the formula for current is, if I think about V is equal to IR, right? The basic Ohm's law formula. And if somebody accidentally short circuit it, so that means connect the positive and negative terminals with a conductor, this can give a really large current because there's no external resistor. The resistance of the connecting wire is relatively low, so you can get a really large current which can be dangerous. So to reduce this risk, when power supplies are made, you introduce some internal resistance as a part of its construction. Now let's consider a very simple circuit. You have a power supply of EMF E, and internal resistance is R. The external resistor here is capital R. The potential difference across it is V, and the current in the circuit is capital I. Now, the current capital I is the EMF divided by the total resistance. In this case, the total resistance is external capital R plus the internal resistance lowercase r. So here's the first thing you need to know. I is equal to E over R plus R. The second formula is a kind of a derivation that comes from this one. So I'm going to move this R plus R to the left hand side. You get capital R plus lowercase r is equal to A. Now let's multiply out the brackets. I times capital R is IR plus I times lowercase r is I lowercase r is equal to E. Now we know V is equal to IR, so that is V. So I can get the next version. V is equal to E. I'm going to move it to the other side, minus IR. So many exam questions about simple circuits can be done with these two formulae. I equals E over R plus R and V is equal to E minus IR. Here's an example. Please pause the video and work out the size of the current and potential difference across the external resistor, or we call it terminal PD. So the first part is very straightforward. All you need to do is just substitute in the formula. I is equal to E over R plus R. E is the EMF, which is 20, divided by the total resistance is 39 and 140. So the current is 0.5 amps. Then to get the terminal PD, let's put it in the formula. V is equal to E minus IR. Substitute the values and you can see the terminal PD is 19.5 volts. Now, here is something really interesting that you need to observe. The EMF of the cell is 20 volts. However, the terminal PD is a bit less than that. It's 19.5. So can you see, there's like 0.5 volts is kind of not coming out. So we call this, within inverted commas, lost volts. It's not really lost, but we call it lost volts. So in this example, it is 20 take away 19.5, which is 0.5 volts. Now, what really happens is, if you think about it, this 0.5 is actually kept across the power supply to drive the current through the 1 ohm internal resistor. If you use V is equal to IR, you can clearly see for a current of 0.5 amps through a 1 ohm resistor, it needs to keep 0.5 volts across it. Here is a simple experiment to find the EMF and internal resistance of a cell, and you can get exam questions on this one. So here you have an power supply, EMF and internal resistance are not known, we are going to work it out. You need an ammeter, voltmeter, change the resistance of this external resistor, and then you can record the voltmeter and the current reading. So you need to change it again, you get a different value for the voltmeter and current. So in physics, to produce a valid graph, you need to get a minimum of 6 pairs of reading. If you can get more, that's okay, but minimum of 6. Then we are going to produce a graph of V against I. When you produce the graph, you get it in this shape. So let's see why you get this shape. So V is equal to E minus IR. Now I can see V is in the y-axis, so let's leave it there. But I have to kind of do a little bit of rearrangement on the right-hand side. So V is equal to minus RI plus A. And now you can clearly see, oh, this is y equals minus mx plus c type, which is the shape of the graph. Now you can clearly see the gradient of the graph gives you the internal resistance, and the intercept gives you the EMF. So it's very easy to figure this out. So this value here gives you the EMF, and the gradient of the graph can be used to work out the internal resistance, lowercase r.